Pat Dragon's math writing class is voting on the most interesting number. Several numbers have risen to the top as the most popular candidates. These numbers are 2, 4, 1, 19, 3, and E. Although the class was ready to start voting on the most interesting number, several students began to wonder, what is the best way to vote? The students in Pat Dragon's Math 370 class want to make sure that they are not making any biased errors when determining the most interesting number. Some students in the class think it is best to start the voting process by splitting the class into groups that can vote on their own number representative. The class decides to try this approach, but some are concerned about how the new voting groups will affect the voting results. The voting must be fair, organized, and representative of the voters' choices. In order to allow for this, we must first and foremost talk about gerrymandering. The students have decided to split their class into groups in order to get a representative for each group. The question is, how do we split the class into groups that are fair, and how does how we split the class affect our outcome? The class decides to try out some small-scale examples in order to see the effects of gerrymandering. Before splitting their whole class into groups, say there are 12 people in the class and 8 people vote for 4, while 4 people vote for 2. We want to split this mini-class into 4 groups. Looking at the voter distribution, it seems we have 2/3 of the class voting for 4 and 1/3 of the class voting for 2. In order to have a fair grouping, we want our representatives to closely match what the voters want. In order to do this, these are the groupings that the class decides is the best way to split the class. With this setup, 4 wins 3 groups, while 2 wins 1 group. Looking at the pie graphs of these results, we can see that the voters and the representatives have very similar proportions, not exactly, but close. The voters of 2 won 1/3 of the vote and won 1/4 of the representatives. One of the students in the class is unconvinced that this grouping is the best way to split the class. He decides that splitting the class into 4 rectangles may be the best way to split the class. This way, 4 wins all 4 groups. Looking at the pie graphs of these results, the class notices right away that choosing the groups this way completely shuts out the possibility of 2 getting any representatives. Although just choosing rectangular boxes may seem like a fair way to split up the class, it does not give us a fair representation of what the voters want. Based on these examples, the class realizes that whoever draws the districts has control over who gets the most representation. If a 4 supporter drew the districts, they could draw them like the previous example and screw the results drastically. So the question remains, how do we know when we've split our class into fair groups? There is actually an algorithm for this called the shortest split line algorithm. The algorithm takes bias out of the question and splits the population into n number of districts using the shortest line possible. Although this does get rid of bias, it does not change the fact that unrepresentative groups could be created by this algorithm. The key of this algorithm is using the shortest line possible. If n, the number of groups you want to split your population into, is even, then you will first use the shortest line possible to split the population into 2 n divided by 2 sized groups. Then, split the 2 groups in half with the shortest line possible. Continue this process until you get n number of groups. If n is odd, then you take n divided by 2, and the 2 integers that n divided by 2 lies between is the proportion that you want to split your population into. Here is the class, assuming we know what number everyone is voting for. The students want to split the class into 7 groups using the shortest split line algorithm. In order to do this, the students know that 7 is an odd number of groups, so they divide 7 by 2 to get 3.5. This means that the proportion they want to split their class into is 3/4. The total number of students in the class is 35. To use the shortest split line algorithm, we must split the class into a 3/4 ratio with the shortest line possible. The students notice that the shortest line is here, with one side having 15 students and the other side having 20 students. We can see that dividing the class into a group of 15 and a group of 20 is a 3/4 ratio, because when we divide 15 by 20, we get 0.75, which is the same number we get if we divide 3 by 4. Thus, the class is split into a 3/4 ratio. Now we must split both sides into smaller groups. On the right, our ratio of 3 is odd, thus we divide 3 by 2 to get 1.5. Therefore, the right side needs to split into a 1:2 ratio. The students find that the shortest line that can do this is here. splitting the group into a group of 10 and a group of 5, giving us a 2-1 ratio. On the other side, the class notices that our original ratio was 3-4, meaning on this side we will be splitting the group into 4 groups. 4 is even, so we first split the group into 2 groups of size 10. The shortest line that accomplished this is here. Now we will split our groups into even smaller groups. On the left side, the students notice that the ratio before was 1-2. The group that had a ratio of 1 is done, but 2 is even and must be split into 2 groups of size 5. The shortest line that can do this is here. Now on the right side, we still need to split the 2 groups in half, so there are 4 groups of size 5. The shortest lines that can do this are here. Thus, the students have split the class into 7 groups, or districts, that can vote on the most interesting number and gain representatives. In Pat Dragon's Math 370 class, it seems that 19 wins 4 groups, 1 wins 2 groups, and 3 wins 1 group. The class agrees that the shortest split line algorithm is a good solution to the problems of gerrymandering.
Pat Dragon's math class now wants to look at different voting systems. Before we start that, let's first discuss what a Condorcet winner is. A Condorcet winner is the candidate that would win against all other candidates running in a head-to-head election. We are now going to look at an example of a Condorcet winner. Suppose Pat Dragon's class is holding an election to determine the best number. The candidates are 1, 4, and 19, where the winner is determined by the candidate with the most votes. Suppose the votes are distributed as follows. Note that 4 wins the election with 9 out of 18 votes. In this election, 1 is a politically similar candidate to 4, and if 1 was not in the election, the voter who voted for 1 would have voted for 4. As 19 is on the opposite side of the political spectrum, if 19 was not in the race, his voters would be split between 1 and 4. Looking at the head-to-head election of 4 versus 19, we can see that 4 wins the election when 1 is not in the race. Now looking at the head-to-head election of 4 versus 1, we see that 4 also wins this election. Note that 4 is the Condorcet winner since 4 won head-to-head against both 1 and 19. It should be noted that not all elections will have a Condorcet winner due to the variance in voter preferences.
The class now gets back to thinking about voting systems. Here we'll look at the most popular types of voting systems to try to get a feel for how they function and what attributes each of them have. The 4 major systems we're looking at here are called plurality, approval, board account, and instant runoff. We'll be using simulation results to compare these systems. An example simulation output is displayed here. One reads this output like a political compass. The X and Y axes represent individual political spectrums. Each colored dot represents a particular political candidate and where they lie on the compass. The colored area of the compass corresponds to the color of the winning candidate. We're assuming that political opinion is normally distributed in this simulation. We would expect that if the political opinion were centered on a candidate, that the candidate would win. Such is the case in the example provided here. So to start off, we have plurality. Each voter votes for only one candidate, and the candidate with the most votes wins. It is the simplest system and is typically what most people think of when talking about voting. Unfortunately, it does not meet the Condorcet criterion, is susceptible to strategic voting, and gerrymandering is very easy to do. We can see the effects of wasted votes in these graphs. The candidates in the middle get squeezed out, since even though public opinion is centered on them, the other candidates are close enough such that the tails of the distribution make up the majority of the voter base.
We are now going to explore some problems of the plurality voting system. We previously looked at an example of a plurality voting system producing a Condorcet winner. Although we will not go through an example, we should know that this is not always the case. Instead, let's first look at minority rule. Minority rule is when the ruling class was elected by a small percentage of the overall population. For example, let's consider our example with Pat Dragon's Math 370 class. Suppose once again 1, 4, and 19 are running for the most interesting number, and Pat Dragon will use a plurality voting method to determine the winner for this election. Suppose that the votes look as follow. Observe that 4 wins this election with a minority number of votes. This is an inherent problem of plurality voting systems and causes plurality voting systems to turn into two-party systems since underrepresented political groups realize that they cannot win elections and have to compromise on who to vote for. We will now be talking about political diversity. We define political diversity as allowing new political parties to appear without disrupting the outcomes of an election had that political party not been present. To explain this, let's consider an example. Suppose last year, Pat Dragon's class voted between 4 and 19 to be the best number, and 4 won with the following distribution of votes. This year, some voters who had previously voted for 4 are sick of how 4 has acted as the best number. This year, some 4 voters decided to back a politically similar but less popular candidate won. The votes are in, and the results look as followed. Notice that 19 wins this year, while if 1 had not run, 4 would have won again. This phenomenon is known as the spoiler effect, and it makes it difficult for third parties to become popular in a plurality voting system.
Approval voting performs a bit better. Each voter votes for any number of candidates, and the candidates with the most votes wins. It is still a fairly simple system from the voter's perspective, but not so simple that it's easy to gerrymander. Because it accounts for multiple preferences, it does not produce a spoiler effect. It also meets the Condorcet criterion. As an example, here are 5 voters and their votes. Each voter can choose any number of candidates. We see that 1 has 4 votes, 4 has 3 votes, and 2 has 2 votes. Thus, the candidate 1 wins. Here are the approval simulations with the same initial values as before. We can see that the center candidate has gained an area for themselves, and that the graphs look like they're determining who wins by selecting the candidate that has the least Euclidean distance from the mean political opinion. In board account, each voter ranks the candidates. The candidates are given points based on their ranking. The candidate with the least or most points wins, depending on how you define the point system. For simplicity, I'll have the candidates ranking on the ballot be the number of points awarded, and the candidates with the least points wins. Board account is slightly more complicated than either plurality or approval voting. Although there are instances where it doesn't meet the Condorcet criterion, these instances are very rare. Board account also seems to give preference to moderate candidates, which could potentially be positive, depending on what you're aiming for. Here's an example of a board account election. Each voter ranks the candidates, and the rank of each candidate is the number of points assigned to them. So, for example, counting the points of candidate 4, we get 1 plus 1 plus 2 plus 3 plus 2, which is equal to 9. We do this tallying for each candidate, and it turns out that 4 has the least number of points, meaning that 4 wins. Like approval, we can see that board account allows for the center candidate to win in these situations, and the space given to the center candidate has increased compared to the approval voting system. Lastly, in instant runoff, each voter ranks candidates. The highest preference candidate is counted on each ballot as a single vote. If one candidate has more than a half of the total votes, then they win. Otherwise, the candidate with the least votes is eliminated, and the ballots ranking that candidate highest are reassigned to the next highest candidate that isn't already eliminated. It is a comparatively complicated system, but it doesn't meet the Condorcet criterion, and it will act in odd ways. In this example, we look at the number 1 ranks of each ballot. There is no candidate that wins more than 50% of the total votes, so we see which candidate gets the least votes. In this case, is the candidate number 2. So we disqualify 2 and then recount the votes using the most preferred candidate. We then see that the number 4 has more than 50% of the total votes, so we can see that 4 wins this election. In the situation simulated, we can see that instant runoff produces some odd results. In some cases, moving the mean political opinion away from a candidate can work in that candidate's favor. Also, it doesn't counteract the squeezing mechanism that prevents moderate candidates from competing, the problem that we have in plurality. At least in the conditions presented in the simulation, this type of voting doesn't seem very desirable.
Alan Gabbard in 1973 and Mark Satterwhite in 1975 presented Gabbard-Satterwhite theorem independently. It concludes that for every voting rule, one of the following three things must follow. The first is the rule is dictatorial, and second is the rule limits the possible outcomes to two alternatives only. The third one is the rule is susceptible to tactical voting. In certain conditions, some voters' sincere ballot may not defend their opinion best. If a voting rule has at least three possible outcomes and if it is non-manipulable, then it is dictatorial. So let's see an example. Consider voters named Alpha, Beta, and Gamma who wish to vote among four candidates named A, B, C, and D. For each ballot, 3 points are assigned to the top candidate, 2 points to the second candidate, 1 point to the third one, and no points to the last one. Once all ballots have been counted, the candidate with most points is declared the winner. So this table means that voter alpha prefers A than B, C, and D. Voters beta and gamma both prefer C than B, D, and A. If the voters sincerely ballot, then the scores are like following. A is 3 points, B is 6 points, and C is the winner, got 7 points, and D is the 2 points. However, voter Alpha can choose another ballot order because she thinks that may defend her opinions better. Assume that she modifies her ballot in order to produce the following situation. Voter Alpha has chosen candidate B as the top one and put candidate C on the last place. Now the scores are totally different. A is 2 points, and B is 7 points, C is 6, and D is 3 points. We can see that B gets the highest points, so B is elected. Voter Alpha is satisfied with her ballot modification because she prefers the outcomes B to C, which is the outcome she would obtain if she voted sincerely.
Thank you for watching our presentation, and here are our references.